Good morning and welcome to lecture 23, and today we will be continuing where we left off in the last lecture, lecture 22, and the lecture 22 we had spent a fair amount of time looking at the two-channel filter bank, the historical development, the polyphase decomposition, and also we started to talk about how to use the linear phase filters, and today we will pick it up from there and we will design the two-channel filter bank using the linear phase constraint. But before that, let us begin with a quick review of the topics that we have covered in lecture 22. I'd like to begin by reviewing the two-channel filter bank, showing that we can write the overall response between x input and output in this fashion, where x hat of z can be written as t of z times x of z plus a of z times x of minus z, and x of minus z representing the term which contains the aliasing. So this you can view as the undesired component, the x of minus z. So the if a of z becomes equal to 0, then we get rid of the aliasing term, and therefore we call it alias free. So a of z equal to 0 is alias free, in which case we are left with only the transfer function t of z, and t of z can be represented in terms of a magnitude response and the phase response. So t e of j omega can be written as mod of t e of j omega e power j phi of omega, where this is the magnitude response and we have the phase response, a combination of these two, and this we have looked at in the last class. Aliasing cancellation, the condition that guarantees that aliasing will be cancelled, where was derived in the last lecture. Again, we will use this in today's lecture as well. F of z equal to h1 of minus z and f1 of z equal to h naught of minus z. So this is the combination, this combination we call as the aliasing cancellation constraint. So equation number 1 is the overall transfer function. If we combine it with the aliasing cancellation condition of 2, then we get rid of a of z. We are left with only the t of z, and today we will look at what are some of the aspects that we will be using to design the filters. So just for completeness, let me write down the expression for t of z. So if aliasing is cancelled, we are left with t of z equal to 1/2 of h naught of z f naught of z minus or plus h1 of z f1 of z. Applying the constraints that we have shown for the aliasing cancellation, this will become equal to h naught squared of z minus h1 squared of z. Okay. Now, as we discussed in the last lecture, 1976 was when an additional observation and a constraint was introduced, that of the quadrature mirror symmetry. So quadrature frequency represents pi by 2, and we design h naught and h1 to have symmetry around the quadrature frequency. So these are called quadrature mirror filters, h naught and h1. If they satisfy the symmetry, then it's called the quadrature symmetry. So the quadrature symmetry is given by h1 of z equal to h naught of minus z. In other words, it's a shifted version of the original filter. If you want to write it in the in terms of the Fourier transform, this can be written as, this can be expressed in the following manner: h1 e of j omega is equal to h naught e of j omega minus pi. Okay, so that is the expression that we want to keep in mind. It's a shifted version. Now, if this condition is satisfied, we now have condition number 3. And with this, we now have the condition of the t of z is now modified to get the following expression, where t of z is equal to 1/2 of h naught squared of z minus h naught squared of minus z. So basically, the entire condition for the expression for the transfer function is now expressed in terms of a single filter h naught of z. So now we would like to look at, in the last lecture we pointed out that if t of z happens to be all pass, then we have eliminated magnitude distortion, but there is phase distortion present. However, if T of Z is linear phase, then we would have eliminated phase distortion. So in today's lecture, we are going to look at how we can eliminate phase distortion in the overall transfer function. So that is our goal for today, and we will develop it. But before that, let us quickly look at a couple of other results that were obtained in the last lecture, just for completeness. If you decompose the analysis filters in terms of the polyphase components, it was shown that the overall transfer function can be written in terms of T of Z equal to 2 times Z inverse E naught of Z squared E1 of Z squared. Now, the conditions that we have imposed are that the aliasing cancellation conditions are present, are satisfied, the quadrature mirror conditions are satisfied, and we have done polyphase decomposition to get this expression. Now we want to go back and look at the case where the transfer function T of Z is a linear phase transfer function. So in the last lecture we talked about what would be the implications if E naught and E1 were delays, what would be the implication in terms of the prototype filter, and we saw that making E naught and E1 as delays will not give us good low pass filters. So let us for the moment we will put aside the magnitude distortion constraint and let us see how we can satisfy the linear phase constraint. So that will be the focus of our discussion today. Overall transfer function is given by half H naught F naught plus H1 F1. Aliasing cancellation constraint satisfied, QMF constraint satisfied, then it will reduce to the transfer function that was presented in the earlier. It will be this transfer function that we will now have to deal with. Okay, so let us just state that for completeness. So this is the transfer function after we have satisfied these conditions. So this is the condition that we have to satisfy. In the reference book that has been suggested for the course, Oppenheim, Schaefer and Buck, there is a section where we talk about the design of linear phase filters, that there are 4 types of filters as we mentioned in the last lecture. If the filter order is n, we can write H of Z as H naught plus H1 Z inverse H2 Z minus 2 all the way to H of n Z minus n. So notice that the filter order is n, and filter order is indicated by the highest power of Z, and the number of coefficients H naught to Hn will give us a total of n plus 1 coefficients. So type 1 polyphase, type 1 linear phase filter has got even order and it has got even symmetry. Type 2 linear phase filters have got odd order and even symmetry. Now let me just maybe it's useful for us to just take a simple example of a filter that satisfies the type 2 constraint, because that will be useful for us in our discussion today. So type 2 linear phase filter. A type 2 linear phase filter, let's take the case where the filter order is equal to 5. In that case, we will get a filter coefficients which are H of Z equal to H naught plus H1 Z inverse, H2 Z minus 2 plus H3 Z minus 3 plus H4 Z minus 4 and H5 Z minus 5. Okay. H5 Z minus 5. Imposing the symmetry constraints by symmetry. Where are the symmetry conditions? Where are the symmetric coefficients? H naught and H5 will be the same. H1 and H4 will be the same. H2 and H3 will be the same. What we will get is a filter which is H naught plus H1 Z inverse plus H2 Z minus 2 plus H2 Z minus 3 plus H1 Z minus 4 plus H naught Z minus 5. And because of the symmetry, if you write down the Fourier transform and express it, we can write this the Fourier frequency response H naught E of j omega, this is H naught, Okay, this is H naught of Z with the symmetry condition, and if you look at the Fourier transform H naught E of j omega, we can show that this is of the form e power minus j omega n by 2 summation k equal to 1 through n plus 1 divided by 2 b subscript k cosine of omega k minus 1/2. Again, this is the result from Oppenheim and Schaefer, so that's the reason why I am not deriving it in this class. I request you to kindly look it up. Now this is a real valued function. Let us make a note of that. Real valued function. It can be positive or negative. It can be, because it is a real valued function, above can be more than 0, less than 0, can be positive or negative, and we can denote this in terms of a real valued function. So basically we can write this as e power minus j omega n by 2 h subscript r, which indicates that it is a real valued function of e of j omega, which is representing the sum of cosine terms. So this is the part that I just wanted to highlight. This is related to what we have been developing. This is type 2 linear phase. This was what was developed in the last class. Just sort of refreshed your memory in terms of what has been developed and what we can do. So now what we would like to do is apply this type 2 linear phase expression with our overall transfer function. That is our task for now. So apply it to the overall transfer function. Let us start on a fresh page. We have the overall transfer function t of z equal to 1/2 of h naught squared of z minus h naught squared of minus z. We have h naught e of j omega given by e power j omega n by 2, e power minus j omega n by 2 h r of e of j omega. Let us just get the expressions and then substitute. So h naught e of j omega magnitude squared will be equal to e power j omega n by 2. That term will go away because we are taking the modulus. This will be h r e of j omega magnitude squared. Now h naught of minus z, h naught of minus z evaluated on the unit circle, h naught of minus z evaluated on the unit circle can be expressed in the following manner. This can be shown to be equal to h naught e of j omega minus pi, h naught of e of j omega minus pi. So now substitute the expression for h naught. This will be equal to e power minus j omega minus pi, omega minus pi times n by 2 times h r e of j omega minus pi. Okay, that is the expression that we have. And if you take modulus squared, we can then show that what will be the expression that we will have. Okay, so now what we need here is not h naught magnitude squared, but what we need is h naught squared. So let us substitute and obtain the expression. So this will be half h naught squared. So that will give us e power minus j omega n times h r e of j omega squared. That is the first term. The second term will be equal to, I want to move this a little bit to the right so that we have more space to express, give the expression. Now we write down the second term minus 1/2 of h naught squared of minus z. So if you want to write down that step, h naught squared of minus z, that will be equal to it will be the squaring of this expression, e power minus j omega minus pi times n HR squared e power j omega minus pi. Okay, so that is the expression. But note an important one, we have assumed type 2 linear phase. So therefore n is odd. So if you now expand this expression, this will be e power minus j omega n e power minus j pi n. E power minus j pi is minus 1, and the term here is HR squared e power j omega minus pi. Just a quick simplification of this term. This is nothing but minus 1 raised to the power n, where n is odd, is equal to minus 1 since n is odd. So therefore, if you now want to substitute back into this expression, what you will get is minus sign from the minus 1 e power minus j omega n HR e of j omega minus pi whole squared, or write the h write it in here, h squared. Okay, so this is the overall transfer function that we have. It can be simplified, and we can obtain some very interesting insights into the expression that we have just now derived. So we can take the 1/2 and e power minus j omega n outside. What's left within the brackets is HR squared e of j omega plus, notice that the minus and minus will cancel each other, giving us a plus sign HR squared e of j omega minus pi whole square. Okay, so this is the overall transfer function if H naught happen to be a type 2 linear phase transfer function. So let us just now assume, we have assumed the H naught of Z is a type 2 FIR linear phase transfer function. Then in that case, the overall transfer function T of Z comes out to be of this form. Very important to note that this is a real valued, and what we have here is a term that is linear in terms of the phase. Linear phase. You can see that the phase grows linearly as omega increases. So what we now have obtained is a transfer function for the 2-channel filter bank, where the overall transfer function is linear phase, and therefore in this under this condition, the phase distortion in T of Z has been removed. Phase distortion in T of Z is eliminated. However, we are still left with the transfer function HR squared e of j omega plus HR squared e of j omega minus pi. Now that could have some magnitude distortion. So how will we deal with that? So here is a summary statement, if you will. Aliasing cancellation implies aliasing is removed. Aliasing is removed or eliminated. Okay, so that is point number 1. Aliasing cancellation constraint will remove aliasing. So that's number 1. Second, we have made the assumption that H naught of Z is a type 2 FIR linear phase. This implies that phase distortion is eliminated. Phase distortion in T of Z. Phase distortion in T of Z has been eliminated or removed. Eliminated. So what we are left with is only the magnitude of the transfer function, so which would be the magnitude response will be T e of j omega the magnitude response, we would like it to be as close to a constant as possible, as close to like an all pass filter. So this is the is equal to constant for all values of omega, and we will put a question mark. Are we, how close can we satisfy this condition? So that is what we are going to be looking at and trying to understand and then try to implement. So let me summarize what we have said so far. We started out with the 2-channel filter bank. We said that we can enforce the aliasing cancellation constraint to eliminate aliasing, which leaves us only with the transfer function T of z. Now, T of z has got a magnitude component and a phase component. The magnitude component we showed can be eliminated if the overall when we wrote the polyphase components, we showed how the magnitude components could be magnitude distortion could be eliminated, but that led us to filters that were not of very good quality. So therefore, for now we said let's leave aside the magnitude distortion, let us look at the phase distortion. So going back to the original structure, applying the QMF constraint, we now said, and the fact that the analysis filter H0 will be linear phase transfer function. We said that we will pick the type 2 transfer function, and then showed that this would be the case of the overall response. And we now have the fact that aliasing has been removed. We now have H0 of z as a type 2 linear phase transfer function, type 2 FIR linear phase transfer function. So we showed that the phase distortion has been eliminated, and now we would now like to see how we can eliminate the magnitude distortion as well. So the task for the rest of the lecture is to develop a system where we can design the filters to minimize the magnitude distortion. So the magnitude distortion or the magnitude response we can describe or write it down as Te of j omega magnitude is equal to 1/2 of H0 E of j omega magnitude squared plus H1 E of j omega magnitude squared. So that is the response. We are going to design it with the type 2 linear phase filters, and now we go back into the filter design component, which I am sure you would have studied in digital signal processing, but we will just highlight the parts that we would need for today's discussion. Okay, so typically in the design of a filter, FIR filter, we would introduce 2 criteria. One is the pass band criterion, and there would be a stop band criterion. Now stop band criterion, let me just sketch the requirements, and then we can proceed with the aspects of the design. So this is the design of FIR linear phase real coefficient filter. So we have the filter response to be as flat as possible until we reach omega p. This is the pass band edge, omega p, and then thereafter have a transition band between omega p and omega s, and then from this point on you want the ideal transfer function to be close to 0. But in practice what we would find is that you would have to permit a band around the during the pass band edge and also the stop band edge, and we would like the filter's response, which is the actual filter response, to be contained within this and as close to this as possible. and this is what we would like to design. This is the classical FIR filter design, where you specify the passband edge and the stopband edge. Okay, so the way we would design it is we would first of all compute the passband error criterion. Let's call that as phi 1. This is integral between 0 and omega p, where the deviation of the desired response from of the filter's response from the desired response. Desired response, I am going to write it as dE of j omega minus the response of the filter h naught E of j omega, magnitude squared d omega. Now, in the pass band, we could set dE of j omega equal to 1 for omega belonging to the pass band, from 0 to pass band. Okay, so this is in the pass band region. Okay, so this is basically what is the how much deviation are we seeing from the ideal response from the passband gain of 1. Then we have a second transfer constraint on the stopband edge, stopband performance. So this basically corresponds to computing the total energy in the stopband. We want that to be as small as possible, so that the filter will attenuate the any signal in the stopband. This is given by starting with the stopband edge all the way to pi of the magnitude response of the filter h naught E of j omega magnitude squared d omega. Now, conventional design approach says that we must minimize the combination of phi 1 and phi 2. Conventional design approach says we minimize a combination of phi 1 and phi 2. Let us call it alpha times phi 1 plus 1 minus alpha times phi 2, where alpha is a real valued constant which is some between 0 and 1. So therefore, you have given weighting accordingly. You can give half and half, which means you get equal weighting, or you can give 0.7 and 0.3, any combination we can do. So if you are more interested in the pass band, give more emphasis on the pass band error, or if you are more interested on the stop band, give more emphasis in the stop band, on the stop band side. Now, this is conventional low pass filter design. How is it different when we want to design a filter for a 2-channel QMF bank? So that is the task that is before us today. So we said that in the case of a 2-channel filter bank, we are trying to minimize the magnitude distortion, and therefore the condition that we would like to minimize, let us call it as in terms of a third objective criterion, which is given by in the entire band from 0 to pi, in the whole band, we would like the transfer function to be as close to a constant as possible. So this would be equal to 1 minus the magnitude response. The magnitude response that we are talking about is mod TE of j omega squared. Okay, so this is the magnitude response TE of j omega. This is the magnitude response, and we would like this to be equal to we would like this to be as close to 1 as possible. So basically, we want to minimize this. So 1 minus TE of j omega magnitude whole squared d omega. Now, this we can write it in terms of the components of TE of j omega. This can be written as 0 to pi 1 minus mod of h naught E of j omega magnitude squared minus h1 E of let us write it in terms of h naught itself, h naught E of j omega minus pi magnitude squared, and the whole squared times d omega. So this is the overall objective function phi 3. Now what I want you to visualize is the following. If you go back and look at the design of the filter, we have this as the constraint for the classical filter design. Let's take a closer look at that. Okay, so we have here the classical filter design, but now can we onto this one, can we map the constraint for the what we call as a flatness constraint, the condition that we are trying to minimize the magnitude distortion completely. So here is what the response or what we are trying to achieve, what it looks like. So we have H naught E of j omega, which has a certain response, and we then have H naught E of j omega shifted by pi, and this frequency is pi, and so this is the complete system scenario. Now between 0 and pi, in this band of interest between 0 and pi, we are measuring the deviation from a constant. So we are taking H, this is H naught, this is H naught E of j omega minus pi, the shifted version. This is H naught E of j omega. We want to take magnitude squared and then add them together. Now if this is close to 1, magnitude squared, let's look at the magnitude squared response between 0 and pi. This is going to be close to 1, in this region. It's going to be close to 1 in the pass band region, in the stop band region. Now where things are not so certain is in the transition band. So the question mark basically lies in what happens in this band. It could happen that you could have a flat response here, but it could also happen that you may have a bump, upward bump, and then it becomes flat after that. Or you could also have a scenario where there is a depending on how much overlap you are allowing, there could be a bump. So in some sense you could visualize it like this. If you had the blue response, you had a flat constraint. Now if it turned out that you had the green response comes when there is a wider transition, and therefore there is a dip in the so the transition, let us say, is a little bit wider than so the transition is wider. Now when do we get a bump? When the frequency responses possibly are sharper, overlapping more. So therefore the I use the orange. Okay, so all right. So this is the, let me change this to, let me just draw it with orange. So this could be the case when you get a bump here. So okay, so orange corresponds to the case with orange. The blue line corresponds to the one with the blue, which is almost flat over the entire response, and then you have the green case where there's a little bit of a bump. Now yes, we don't know ahead of time how to design the pass band and the stop band, but this is what we will do via the optimization method. So here is the optimization step, or the step of that we have to do the computation. So notice that we have to apply the following condition. We want to have a very good flatness constraint in the over the entire frequency band, and that will be to a large extent satisfied if you have a good stop band condition, because if there are large ripples in the stop band, you will notice that the flatness constraint will also get affected. So therefore, we now have two of the constraints. Phi 2 is given by 0 from omega s to pi, the stop band energy, omega s to pi mod of h naught e of j omega magnitude squared d omega. And phi 3 is the flatness constraint that we have discussed in the last slide, and let me just copy that and capture it in the current slide for completeness. Okay, so here it is. Okay, so we have these two constraints. Now the question is, do we still need the passband constraint? It turns out that the passband constraint is not needed anymore for the following reason. Because if you visualize the ripple here, the ripple is of this form. This ripple is nothing but the stop band ripple of the original filter. Notice the stop band of the, when you shifted it by pi, now this overlaps with the pass band. So as long as we have optimized the stop band of the filter H naught, the shifted version will ensure that this is small in this region, and therefore the pass band has got very little ripple, or is as flat as possible. So the overall weighting function that we now need to employ does not require the pass band, but however needs the stop band, and it needs it requires the flatness constraint. So alpha times phi 2 plus 1 minus alpha times phi 3, or you could write it the other way if you want. Doesn't make a difference. So basically it's a weighted combination of these two, and this is what will help us satisfy the condition that we are looking to have. So therefore, what are we doing? We have designed a FIR type 2 linear phase filter, type 2 linear phase filter with both the stop band constraint phi 2, and so this would be the stop band constraint, and we also have the flatness constraint. The flatness constraint comes from phi 3. This is the flatness constraint. Combination of these two have been used to get the desired filter, flatness constraint. Okay, so when we use this, we have aliasing cancellation guaranteed. We then have the phase distortion. Phase distortion is completely removed because this is a linear phase filter. Phase distortion eliminated in T of Z. Now what is the only thing left is magnitude distortion. Magnitude distortion is the magnitude response of TE of j omega, and how much it deviates from a constant. That more or less comes from phi 3, and this is what the response will look like. You have a very flat response in the region of the pass band, then maybe a small bump where the transition band occurs. So if this is pi by 2, this is where the transition band will occur. This is pi, this is 0. So around here maybe a small bump, and then it remains flat for the rest of the. So basically we have something that is approximately flat. It's not exactly flat, but it becomes approximately flat. So this is a very powerful result which we are able to to leverage for our designs. So the two-channel filter banks, filter bank using the linear phase filters was a very popular method. Filter bank using the linear phase type 2. This was very popular because it gave us a way to design filters that did not have aliasing, did not have phase distortion, and had very minimal magnitude distortion, which we could then optimize with respect to the condition that we have. Okay, so now we can summarize the total results that we have in the following manner. The two-channel filter bank, using the linear phase type 2 filters, we are able to eliminate magnitude distortion, eliminate phase distortion and aliasing cancellation, and also we just have a residual magnitude distortion as was shown in the previous graph. So we now have a method where we can design the two-channel filter bank to a large extent satisfying the requirements. But let us make the note that magnitude distortion has been significantly reduced, but not eliminated, because we have to still satisfy the flatness constraint, and the flatness constraint is only approximately satisfied. It's not exactly so significantly reduced but not eliminated. Okay, so that is the situation with the two-channel filter bank at the. So we are still interested in methods that can completely eliminate the magnitude distortion. Now that is something that we will take up in the next lecture. But before that, I just want you to think about the constraints that we had posed. We had posed the constraint that it must be a type 2 on the constraint on H0 of Z. It must be a type 2 FIR linear phase. Okay, now type 2 we know has got odd order, n is odd, the number of taps is even, and it has got even symmetry. Okay, now there is a type 4 FIR linear phase which has got n odd, which has got n plus 1 even, and it has got odd symmetry. Now could type 4 have been used? Why not type 1, type 2? Why not type 1? Why not type 2? Okay, these are very crucial questions in our understanding of the design process. Notice our overall transfer function was of the form Te of j omega equal to 1/2 of H0 squared E of j omega minus H1 squared E of minus j omega. Okay, so this overall expression very important for us to keep in mind, because this we simplified and then obtained it because of type 2 assumption. Because of type 2, we got it of the form Te of j omega is equal to 1/2 of HR E of j omega squared plus HR of E of j omega minus pi whole squared. So we were able to reduce it to this form E of j omega n, and then when you took the magnitude response, you got the expressions. So this is very, very important, because only then we can get the flatness constraint. You will find that if you choose other combinations, we will not be able to satisfy the flatness constraint. That is an important element that I wanted us to keep in mind. Okay, so the summary that we can then put forth is that we have been able to design a 2-channel filter bank where we have type 2 FIR linear phase, and we have been able to capture the flatness constraint. We are able to eliminate the aliasing, also the phase distortion. Now, what I would like you to do is try the design example that is presented in the textbook P.P. Vaidyanathan in section 5.2.1, example 5.2.1. This is a design example where we have you can use MATLAB to design the filter that we are looking for. Remember, it's a type 2 linear phase filter. So we are choosing n equal to 31 and stop band edge omega s as 0.586 pi. And if you can then look at the design the filter through optimization, and then show what is the stop band attenuation that you have for H naught. So basically you would have to design it with the overall constraint as alpha times phi 2 plus 1 minus alpha times phi 3. This is the filter response. The response, we are looking at what is the maximum minimum stop band attenuation, AS. In the particular example that has been given to us, we can please try it out and verify that you are getting something which is very similar to this one. So delta 2 is the maximum deviation. So this is delta 2, AS equal to minus 10 times log base 10 of delta 2, and this is approximately of the order of 38 dB for the filter that has been designed for the 2-channel filter bank. And the deviation from a constant. So if you look at 10 times log base 10 of magnitude TE of j omega, we would like it to be close to 1, as close to 1 as possible. So the deviation, the maximum deviation of this expression from 0 dB, from the what we want as a purely flat constraint, from 0 dB. So in other words, the same structure, let me draw this. This is 0, this is pi. Ideally we would like it to be a constant at 1, which is equal to 0 dB. Now when we plot the response of the TE of j omega, there will be some variations from here, and probably the maximum variations occur around pi by 2, and then you have this. So basically we are measuring the maximum deviation from 0 dB, either on the positive side or on the negative side, and this comes out to be plus or minus 0.025 dB. So we can see that the from this particular design example that you can get filters with good stop band attenuation, and also satisfying the flatness constraint to a very large degree. Now it is very insightful for us to also compare this particular design with the traditional linear phase FIR design. So if you are able to use MATLAB and are able to use the equiripple filter design, FIR filter design, equiripple FIR filter design. This is also known as the Parkes-McClellan filters, Parkes-McClellan. So a filter design. please see what is the condition that we can achieve if you pose the constraint on this, where the filter length is equal to 31 and omega s is of the order omega s is of the order of the same as before, 0.586 pi, and what is the best value of the stop band attenuation that you can get. What is the best stop band attenuation? So you can just get a feel for if you did not have the flatness constraint, what would the filter design look like? If you had the flatness constraint, what would the filter design look like? And therefore we are able to get the response. Now there is a very important observation that we can make, and the observation can be summarized in the following manner. The observation is that the pass band and the stop band edge, when we are designing the filter bank, are not independent of each other. So here is the observation: the omega p and omega s for a two-channel filter bank, H naught E of j omega. So H naught E of j omega is a filter being designed for this. Notice that there is a stop band edge that we have to worry about. So flatness constraint, and then a stop band edge, and then there will be some ripple. Now, because of the constraint that we have, the shifted version will be basically shifted by pi, and this is pi, and this will have the same stop band edge. Now, the portion where the squares of these two must be a constant, right? The squares sum of these two must be a constant, must be as close to a constant as possible. Okay. Now, because this is already in the stop band, the pass band is guaranteed. That is why we said we don't need an additional pass band constraint. So if the stop band is the frequency at which the frequency response becomes very small, then by symmetry we observe that the pass band will also be related to the stop band, or in other words, omega p will be equal to pi minus omega s. Basically the frequency at which you start where the stop band begins is related to where the pass band ends, because of the flatness constraint. So this is because of the flatness constraint. So again, this is just an observation. It's good for us to know that how will the pass band and the stop band be related in the filter. They will have symmetry with respect to the quadrature frequency because of the flatness constraint. Now, one last aspect, just like I had asked you to answer the following questions. Why type 2? Why not any of the other types? Why not other things? So here is an example which I would like you to look at and also try to analyze, so that we can then get a better understanding. Look at the following structure. It is a two-channel filter bank with a slight difference from the one that we have studied earlier. H naught of z downsampled by a factor of 2. On this branch we have a delay z inverse followed by H1 of z followed by a downsampling by a factor of 2. Okay, and then of course we will have the upsampling and the synthesis filters. Let us draw the complete picture. Then picking it up from here, we have the upsampling by a factor of 2. Upsampling by a factor of 2. Look at the synthesis filter f naught of z. Upsampling by a factor of 2. And synthesis filter f1 of z, and the two signals then combined via a delay added together producing the output. Okay, so this is output as x hat of n, input as x of n. What I would like you to do is look at the overall transfer function, write down x hat of z in terms of t of z times x of z plus a of z times x of minus z, just like we did before, and then obtain the conditions for aliasing cancellation. What are the conditions that must be satisfied? Condition for aliasing cancellation. So, this is the task number 1. Now, if we want to eliminate the phase distortion, we will want to go for a linear phase. So, H naught of Z has to be linear phase, Now, is it type 1, type 2, type 3, type 4? Which of these types will work? Will type 2 work for this case also? Type 1, 2, 3, 4. Which one of these will work? And it is very instructive for you to go through this example and then try to answer the question, how is the linear phase property being utilized, how is the flatness constraint being achieved, and thereby overall a system which is got no aliasing, no phase distortion, but only minimal amounts of magnitude distortion which is obtained because of the design methodology that we have used. So, we will stop here for today's lecture, and in tomorrow's lecture or in the next lecture we will then begin, or we will start to look at ways of eliminating the magnitude distortion. So, next lecture, so we would look at the 2-channel filter bank. We of course want to have aliasing cancellation to be done. We want magnitude distortion elimination, just like we have eliminated the phase distortion in today's lecture. Can we look at the magnitude distortion elimination? So, that will be the second, what will be the lecture that we will be picking up in tomorrow's lecture. Thank you very much.